Okay, hello, my name's Eric. We're back for another review after completing a unit in a second year algebra class. And the topic that we're reviewing, boy, it's pretty spread out. There's transformations of graphs, there's graphing, square root, cube root, fourth root functions, and so forth. There's also solving equations that have square roots and cube roots and so forth in them. And then we even get to solve a nonlinear system and locate the graph of a circle. So if you need help with any of those things, that's what you'll see in this video. The first question in this review asks us which of the four graphs present here is the graph of square root of x minus 5. All right? Scroll that up just a little bit so you can see it better. Which one? Well, you can go to Desmos or some graphing utility to help you figure that out. It looked to me like they were subtracting 5 out here, outside of the square root. And so I have a slider set up so you can look and see what that would do. If I have minus 5 out there, it's basically transformed this graph vertically down 5 units, so it should look like that. Sometimes we get confused between that kind of a transformation and this, where if I subtract 5 in here, it moves off to the right 5 units. So anyway, I think the answer is going to be that we should expect a vertical downward translation of 5 units, and that looks like this one. So I would go ahead and check this as your selection, and we'll keep moving here because we have a big variety of things to cover and just a few minutes to get it done. Problem 2. Some function f of x is just a plain square root of x. We know that looks like this. I just showed you one of those. It's a half of a rotated parabola. And what's going to happen to this if I add 1 and add 8? Let's see if we can figure this out, and then we'll go back to Desmos and check it out and see if we're right. Okay, what's the plus 8 going to do? A minute ago we saw minus 5 would take us down. Plus 8 is going to do what? It's going to raise us up. So we should get a translation in this direction, 8 units. Then the other thing that should happen is the plus 1 inside of there, that should actually move the whole package to the left 1 unit. If I had minus, it would go to the right inside of there. So I'm talking about this graph translated that way. So a pretty good sketch would look something like this. And I'm going to check Desmos now to make sure that we're right about that. So what do we have? We got plus 1 inside of there. Now why did I put minus 1 on the slider? Because I already have a minus sign. Minus negative 1 makes plus 1. And then for b, I should go all the way up to 8 if it will let me. It takes you almost out of the picture, but if you grab the axes and drag it down, you can see it. And so we were right. Now we're supposed to describe what we just witnessed in words. The graph of g is a translation of 8 units up and 1 unit left. So I would select that second choice right there. Oh, and now I just realized that I forgot to do the questions down here about domain and range. So let me back up. You got some bonus questions here on problem 1. It says, which is the correct graph, and then what's the domain and the range? And so what did we end up picking? Was it this one? Yeah, so domain, like pretty much with any square root function, you can only put positive numbers inside of a square root, or 0, but you can't put negatives in there. And so for that reason, when they ask about domain, they want to know what kind of x's are we allowed to put into this function with the expectation that we'll get a real number out for y. The answer is the domain's got to be x's greater than or equal to 0. And the range would be then the kind of y numbers that you get to see. Well, so let's take a look at this graph. X is 0 here, X is 1, X is 2, X is 3, X is 4. X goes all the way to infinity. But what about the Y's? They start at -5 and get larger. -4, -3, -2. And if you go far enough to the right, this graph will come up and emerge into the positive numbers, even if it doesn't look like it from here. So the range is y greater than or equal to -5. I'm thinking I'm going to check that one. Okay? Moving on. Abstract reasoning. Complete this statement. Sometimes, always, or never, the range of this function is y greater than or equal to 0. Okay, now remember, a can be any real number. They didn't specify that. I think they should have. But what they're saying is, no matter what a you put here, you're going to get a graph that has a range greater than or equal to 0. I can think of a case where that's true. Put a 1 here. Now you have y equals 1 root x, and that's just root x. And we're pretty familiar with that graph, I think. That looks like this. And indeed, all the y numbers that you get to see on this graph start at 0 and get higher. 0 to 1 to 2 to 3, etc. So I'm inclined to say, yeah, that's a possibility. At the very least, the answer is sometimes. So I don't think it's never. I just showed you an example where I can make it work. But is it always true? Pick some a that happens to be negative. So let's go with a equals -2. If you don't know what this does, you might want to make a table of values for yourself. And you'll notice that all the y values that you would get with the square root function multiplied by -2, it makes them negative values. So this graph actually ends up looking like not exactly a reflection, but a reflection and a vertical sort of dilation, that wouldn't be the word, a vertical expansion of this graph. So reflect over the x-axis and expand vertically in this direction by a factor of 2, and that's what you get. Now, does that have a domain of y greater than or equal to 0? It does not. So you can't say always either, so by default, we're going to have to say sometimes. Sometimes. When in doubt, say sometimes. Okay. Graph this circle. The most basic circle equations you can learn are, if you're lucky, the easy ones. They're centered at the origin, and they have a formula like this, or an equation like this. For example, if you see x squared plus y squared equals 25, you can be confident that that will graph a circle, a full circle, and the radius is pretty easy to figure out if you just write this perfect square as the square of 5. So that's a circle centered at the origin with a radius of 5. I can't quite tell on this one yet, though, because it doesn't look exactly like this form. So we'll do a little bit of cosmetic work to it quickly here. We will add y squared to both sides, and that's going to look like this. And then if it makes you more comfortable, reverse sides around the equal sign. You can use what's called the symmetry of equality. Write the equation backwards. And then you might as well think of 1 as being 1 squared. Okay, it should be pretty clear now that this is a circle centered at the origin with a radius of 1. And you're expected to draw this? Yeah. Yeah, just do something like that. Okay. And then you can just sort of see how this circle would come around. It doesn't have to be gorgeous. It's got to look a little bit like a circle. Good enough. I'm moving on. Problem 5. Does this graph represent a square root or a cube root? Okay, we've graphed square root functions before, and you know they look something like this. The first time I ever had students graph this, I told them to take the positive values in the table of x squared. So I'm talking 0, 1, 2, 3, 4, positive x's. Write the answers over here to the squares. And then I just said, reverse the x's and the y's. Make what's called an inverse function. So now, the x, y's look like this. And that's what a square root graph is. That's how it can be made if you're not familiar with it. And then you just go plot those points. So this is how you get numbers for a square root graph if you want to plot them. You can do the same thing with a cube root, but on the cube root you don't really have to exclude the negatives. Because on a cube root graph, you start with x, and you go ahead and put some negatives in here. And you cube both sides, or excuse me, cube all the x's. So you're multiplying the number by itself, and you end up getting negative answers like this until you get to 0. And then you start going 1 times 1 times 1, 2 times 2 times 2, 3 times 3 times 3, etc. Now, if you graph this, you'll get a classic cube function. Looks like this. If you turn the table around, you'll get all of these numbers backwards, and you'll get a graph that looks like this. So the first thing I see when I look at this is I'm thinking, if that's related to a cube root function, why am I not seeing this other part of it down here? Maybe it's got more in common with that square root function, which only has one branch. So the way to ascertain and confirm that we're right about the square root is just to go like this. Okay, on the square root function, you get a point 0, 0, and then you get a point 1, 1. Kind of like you see here, 1 over, 1 up. But see, that's true on the cube root function also. However, on the square root function, you get an ordered pair like this. 1, 2, 3, 4, and then 2. And compared to the last point, it's 3 to the right and 1 up. And that's exactly what's happening here. 3 to the right and 1 up. And there's different ways you can convince yourself, but you should. And in fact, that's the answer. This is a square root function. Square root function, okay? All right, let's not make this take too much longer here. Scrolling. We have some equations we have to solve here, starting with this one. Yeah, you always have to be careful when you solve square root or fourth root equations, because you'll get in the mechanics of it. The mechanics tell you, you want to solve this, you have to square both sides. You have to go like this. And that's how you're going to do it. The danger is, though, that sometimes when you square both sides of an equation, you throw in an answer that's not really an answer. It's sometimes called an extraneous solution. It looks like an answer, it smells like an answer, but it's not an answer. And what's the reason for that? Well, is -5 equal to 5? No. But if you square both sides, suddenly you get things that are equal. Both sides are now equal to 25. So you can take two things that are not equal, and by squaring both sides, you can force them to be equal. And that's really what's going on behind the scenes when I caution you about extraneous solutions. Will we get one here? Oh, we'll see. So we have square root 3x plus 8, and we're going to square that. And why are we going to do that? Because that's going to make 3x plus 8. Then what are we going to do? Oh, I misspoke. That was a 10. Excuse me. Okay, now you're going to subtract 10 from both sides. Like this. And then you're going to divide both sides by 3. And you're going to get x equals 18. You might want to plug it back in to make sure it's really a correct answer. I think it's going to be. But if you got two answers out of this, you might want to check them both and make sure they both really are real answers. Let's check this out. What's 3 times 18? 54. Add 10. 64. Square root 8. Yeah, that's an answer. It works. Okay, scrolling. Okay, remember this little step that I did here with the square root. We're going to do something like that to this problem, but not as a first step. The first thing we're going to do is try to isolate this root. We're going to get things like this 8 and this 15 off of the left side before we do something like taking a power of both sides. So as long as you follow these steps, you won't get into trouble with this problem. Add 15 to both sides. So now you have 8 times the cube root of 10x equals 32. Divide both sides by 8, because I don't want to have this 8 here. Now I have the cube root of 10x equals 4. All right, now don't square both sides because the index of this root is a 3. What you want to do is cube both sides. So you have cube root 10x cubed equals 4 cubed. Cube roots and cubes are inverses. The reason you're doing this in the first place is to take the cube root off. You're going to get 10x on the left, and you're going to get 4 cubed is 64 on the right. You divide by 10, and you're done. And you should not have to worry about whether this is a extraneous or sort of phony answer, because I cubed both sides, and that doesn't tend to produce extraneous answers. All right, 3 more to go. Let's keep it rolling. Problem 8, I already have a square root that's isolated, and so this problem is a little tougher than the ones we've been doing. You're going to go ahead and square both sides. And it turns out that this is actually the easier side, because square roots and square powers are, in most cases, inverse operations. So all that's going to have is 44 minus 2x. But on this side, you have to know how to square that binomial. I'm going to do this quickly. I will note, though, that a lot of students will square a binomial by multiplying it out piece by piece, right? Like x times x times 10, 10 times x, and 10 times 10. Keeping track of all the appropriate minuses and pluses, you end up with x squared minus 20x plus 100. I personally don't use this technique because I think it's slower than it needs to be. You may have learned in first year algebra that when you're solving something that has x squared in it, you want to get everything to equal to 0. So the next step is actually to add 2x to both sides. So you have this, and then you'll almost be there, but not quite. Then you're going to want to subtract 44 from both sides. Why? Because you want to get this equal to 0. and then you want to factor it. So what you're going to do is try to come up with some numbers that multiply to make 56, but add to make negative 18. Now keep in mind, if you're going to multiply to make 56, you have to use two positive numbers or two negative numbers. And let's think about that for a minute. If you use two positive numbers, yeah, you can get 56 one of these four ways, but you'll never get negative 18 in the middle. So it turns out that you want to populate this with negatives everywhere, and then pick this one. Why? Because it not only makes 56 when you multiply, but negative 4 plus negative 14 is negative 18. Then, of course, remember, a factored quadratic expression like this equal to 0 should reveal the roots easily. What number can you put here to cause this to be 0? To wipe out this? Forgot my x. The answer is a 4 would do the job. Whereas over here, if you put 14, you'd have 14 minus 14 is 0. And here you'd have 14 minus 4 is 10, and 0 times 10 is 0. Anyway, the answers are 4 and 14 if they both work in the first place. Well, do they? The answer is no. What? Yeah, one of those is an extraneous solution. I'm going to go ahead and reveal the identity of the bad guy right now. The bad guy over there is the 4. Why? Well, up here, the square root of 44 minus 2 times 4 is the square root of 44 minus 8 is the square root of 36 is 6. But on the other side of the equation, you put the 4 and you get negative 6. Those aren't equal. Well, how is it that then it says it's an answer over there? Well, remember what we did right here? We basically let that 4 sneak in the door. And we're basically taking an equation where 6 equals negative 6, squaring both sides as if everything was equal in the first place. And I think the only answer to this problem that actually works is 14. And I see that's here. Notice that they do put a 4 in here also, though, but don't fall for it. Okay, don't fall for it. Problem 9. It's got a half power. That's like a square root. If you guess that we're going to have to square both sides, you're right. But not yet. First you want to get this expression isolated. So that would look like this. 5 minus x to the 1/2 power. Add 2x to both sides. You get equals 2x. If it's a half power, you're going to have to square both sides. So that looks like this. Square both sides. And you end up with 5 minus x is 4x. Oh, 4x squared, excuse me. This is another equation where I have a square in it, and so you really ought to do everything you can to get it equal to 0. The way to do that is to add x to both sides. This could be and probably should be done in one step. And by that I mean subtract 5 now from both sides. And then, if you can, go ahead and factor this. There are different ways to learn how to factor something like this, but It's either going to go x times 4 or 2 times 2. You don't have an option on the 5. You've got to use 5 and 1. So we'll just think about that for a minute. If you're going to use 5 and 1, I think you have to use 4 and 1, but backwards like this. Put a 1 here and a 4 there. And x and x. And then you're going to want a minus here and a plus here. I don't really want to go through all the explanation of the factoring of that, because that could be a completely separate video, and I'll probably do one like that. But for now, trust me, that's the way you factor this. Let's check it real quick. X times x is 4x squared. 1 times 5 is minus 5, yeah. Most importantly, in the middle, I get negative 4x here and positive 5x there, which corresponds to the 1x that I have there. So anyway, assuming they're both good answers, the answers are 1 here and the fraction negative 5/4 there, which comes from the opposite of this divided by that. All right? Now, are they both good? No, they're not both good. Why not? If you put negative 5/4, also known as negative 1.25, back into the original equation, you'll get a square root here equal to a negative number there. So I'm kind of running out of time, but I'm just telling you, this one's a bad one, whereas this one's a good one. So I would only go with x equals 1. Okay? All right, last problem. Solve the nonlinear system. Okay, now remember, the idea here is that you've got a line and a curve, and you're trying to find their intersection. I may go draw a graph for you of this in just a minute. But one way you can go about this is you can say, look, I already have y isolated here. Y is equal to x minus 2. And so like light bulbs are interchangeable. Think of this light bulb as going bad, you can put x minus 2 in its place. And I'm talking about doing that right here. Yeah, do that right there. So now you have x squared plus, okay, y used to occupy this space. It's going to be taken over by x minus 2, just like changing a light bulb. Then you're going to square this out, and again, I know a lot of students like to do it like this. It sure would be good if we learned a faster way to do this, though. The fast way to do this, square the x, square the 2, make sure it's positive, multiply these two together and double the answer. That's the fast way to do it. But if you do the shortcut, don't forget the middle term, because it often gets neglected and it's just not fair. Add these two together, subtract 4 from both sides, and you get this. You're going to want to factor that. And you factor this not like this. I guess it could be done. But when there's only two terms here and they both have x, you should factor 2x out, which leaves behind x minus 2. And then the roots are 2 for x and 0. Okay, this is where it becomes important that you understand that these are x's, because in this problem, you are looking for ordered pairs. You're not just looking for x's. One of the ordered pairs starts with a 0, and you'll have to figure out what the other number is. The other ordered pair starts with a 2. You'll have to figure out what the other number is. The best place to go to figure that out is here. So if I take the 0 and plug it in there, I get y equals 0 minus 2, and that's negative 2. Plug this 2 in there, and you get 2 minus 2, and that's 0. Pretty easy? Yeah. Anyway, my name's Eric, and I hope you learned something here today. Have a good afternoon.